One kiss is all it takes.
In the world of Bioshock, Rapture is a city unlike any other, a glittering underwater utopia built on the promise of unfettered innovation and personal freedom. In this world, science reigns supreme, morality takes a backseat, and progress comes at any cost. It's here that plasmids were born, special serums made from atom that alter one's DNA, granting them superpowers like the ability to wield fire, telekinesis, and even hypnotize others. But what if this fictional substance had roots in real world science? Could this actually exist in the near future? And could we edit our DNA to enhance the human body? My name is Warm Beef, and I am a second year medical student who loves playing and streaming video games. You can catch me live at twitch.tv/warmbeef. Today, we're going to be diving deep into the medicine behind plasmids and atom from the Bioshock games and explore its possible mechanisms of action through a lens of real world medicine, cell biology, and molecular biology. Before we get into the meat and potatoes of this video, I just wanted to give you guys an update. I really do apologize for the delay on getting this video out. I recently got strep throat, which is a very nasty throat infection. Like, I had the worst sore throat of my life. I could barely swallow, and even speaking for long periods of time was just very irritating. Thankfully, it's all cleared up now, but I just wanted to thank you guys for being patient and thank you guys for the overwhelming support on my last video. Make sure to stay tuned for more videos like this, and I really do hope you guys enjoy this video today. So, what exactly are plasmids and what is atom? According to the Bioshock wiki, plasmids are special serums made from refined atom. In order to understand plasmids, we really need to understand atoms since it's what makes up plasmids. Atom was initially discovered by Bridget Tenenbaum after a sea slug bit one of Rapture's dock workers and miraculously healed their long crippled hand. Atom is a volatile or reactive substance that has the ability to alter genetic material. In particular, it alters the genetic makeup of cells, causing them to become stem cells, which is essentially a cell that has the ability to develop into any type of cell when introduced into a host body. When refined or concentrated, atom is made into plasmids, which can grant users special powers when injected into the body. Unfortunately, the yield of atom provided by sea slugs was not enough to fuel market demand at the time. It was discovered, however, that when sea slugs were embedded into a host's stomach, that it generated upwards of 20 to even 30 times the yield of usable atom to make plasmids. This is what led to the creation of the Little Sister. You may remember them being the ghastly little girls that run around Rapture producing atom and harvesting it from dead corpses. So, atom has stem cells. What exactly are they? Obviously, we can't shoot lightning or fire out of our hands like in Rapture, but stem cells, believe it or not, do actually exist in real life and can be found in many different parts of the body. Often, stem cells are classified based on how potent or how many unique cell types they can become. For instance, totipotent stem cells, called embryonic stem cells, are found inside human embryos when an egg and a sperm meet. These stem cells have the potential or ability to become any cell in the body, like for instance a neuron, a liver cell, or a muscle cell. They also have the unique ability to continually renew themselves so that they can make more specialized cells. And when you think about it, it makes sense since an embryo at some point needs to develop into a full-fledged baby and needs to make every single cell type in the body. Unfortunately, at birth, the number and potency of stem cells we have decreases substantially. Adults still do have stem cells, but they can only develop into a select few cells. For instance, multipotent stem cells like hematopoietic stem cells are found inside of red bone marrow or the inner core of our bones. Although hematopoietic stem cells can't become any cell in the body, they can become any type of blood cell, like white blood cells, platelets, and red blood cells. Similar to totipotent stem cells, multipotent stem cells also have the ability to continually renew themselves, which helps supply the body with a large amount of blood cells throughout our lifetime. Red blood cells on average only live around 120 days. At some point, they need to be replaced, and that's where hematopoietic stem cells come in. Unfortunately, not every cell type in our body has an army of stem cells ready to replenish them. For instance, our nervous system has very limited stem cells. In fact, we only have neural stem cells associated with the hippocampus and the olfactory bulb in the brain, otherwise known as the areas of the brain responsible for memory and smell, respectively. If injury occurs outside of these two areas, our body has limited ability to recover. This explains why injuries involving the brain, like a stroke, which is when blood momentarily stops flowing to parts of the brain, can lead to lifelong paralysis. What's interesting is that certain animals, like salamanders, have the unique ability to regenerate limbs like a tail after being cut off. The mechanism itself is extremely complicated, but at the center of this ability is stem cells. Stem cells rush to the site of injury when a salamander has its tail cut off, and they start making bone cells, neurons, blood vessels, and muscles to help regenerate that lost tail. So, what allows a stem cell to have the ability to become any type of cell? In short, the amount of genetic material it has access to. Genetic material is also referred to as DNA, which stands for deoxyribonucleic acid. It's essentially the blueprint for life. DNA is made up of nucleotides. It's a polymer. Think of it like a paperclip. One paperclip is a nucleotide, but when you take many paperclips put together, it forms a chain of nucleotides, and this is what we call DNA. Nucleotides are made up of three components: a nitrogenous base, a phosphate group, and a ribose 5-carbon sugar. Repeating units of nucleotides come together to make a single DNA strand, and those DNA strands can come together like Velcro to make up one molecule of DNA. Imagine one chain of paperclips linking with another chain of paperclips, and that would make one molecule of DNA, because DNA is double-stranded. Within DNA, there is a code or language, which is made up of a unique combination of nitrogenous bases, which go by the names of adenine, guanine, cytosine, and thymine. They can also be represented with one letter, A referring to adenine, G referring to guanine, C referring to cytosine, and T referring to thymine. With this code, our DNA can create amino acids, which are the building blocks of proteins. It's just like the paperclip analogy. For example, the codon or code AAA, which is just 3 A's, creates the amino acid lysine. Anything that our bodies do can be traced back to proteins and therefore back to DNA, since we need DNA to make proteins. For instance, part of our ability to break down food inside of our stomach is because of the production of hydrochloric acid, or HCl, which is manufactured when proteins in the lining of our stomach pump hydrogen ions and chloride ions into the lumen, or the inside of our stomach. Although every cell in our body has 100% of the DNA that we were all born with, specialized cells only have access to a limited amount of that 100%. For example, a stomach cell, like a parietal cell, which I talked about earlier, makes stomach acid, only has access to parts of the DNA that allows it to do its job. Nothing less, nothing more. It's like if you went to a library that had all the information in the world and you were only allowed to read books in the finance section. Assuming that that was all the knowledge you had access to, it would likely sway you into pursuing a career in finance. So back to Adam. How does Adam make stem cells? Adam is likely a mutagen, aka a substance that can alter DNA and the way that it's used by our cells. A real-world example of a mutagen is ionizing radiation, which comes from imaging machines like X-rays and CT scans. Ionizing radiation contains high-energy particles. When these high-powered particles meet the body, they can easily shoot through the skin, enter our cells and nucleus, where the DNA is stored. Once inside the nucleus, they can collide with our DNA, damaging it. Sometimes this damage can be in the form of breaking both strands of DNA, a single strand, or even producing reactive oxygen species like superoxides. These reactive oxygen species can go around the cell and cause additional damage to the DNA. The net result is that the DNA gets damaged. And when our cells try to repair this DNA, it can sometimes make errors. This could change a AAA, which we know makes lysine, into a GAA, which means that lysine gets converted into a new amino acid called glutamic acid. Depending on the type of protein, this single change in an amino acid could alter the way this protein works, and that's because protein function is so tightly tied to protein structure. As mentioned before, proteins do literally everything inside the body. There are proteins present on our DNA called repressor proteins that literally just sit on our DNA and prevent cell machinery from accessing it for the purposes of replicating our DNA and even for repair. In addition to repressor proteins, there are factors outside of the DNA code impacting the ability to make proteins. We call those epigenetic factors. Examples of this are DNA histones and chemical methylation. You can think of histones as being like yo-yos that wrap around the DNA tightly, packing it, and preventing cell machinery from accessing its information. DNA methylation achieves the same effect, but it's through the addition of hydrophobic or water-fearing chemical groups on the DNA. Specialized cells often have repressor proteins, histones, and methylation on their DNA, which prevent it from accessing the DNA that it does not need for its function. So, for instance, with the parietal cell that produces hydrochloric acid, it would have histones and DNA methylation on the parts of the DNA that it's not supposed to have access to. In order for Adam to make potent stem cells, it would have to get rid of these repressor proteins and interfere with histones and methylation. Doing so would allow the cell to, quote unquote, reprogram back into a stem cell like state, since now it has access to 100% of the DNA again, giving it the ability to become any type of cell. It's like going back to high school and deciding on what career you want to pursue. At that point in your life, you can become anything. This would explain why Adam had the ability to repair the dock worker's crippled hand, since the stem cells replaced his damaged muscle, nerves, and other tissues, and essentially converted his older cells back into stem cells. It may sound like science fiction, but scientists have actually discovered a way to turn specialized cells back into stem cells. This makes a unique type of cell called an induced pluripotent stem cell. Pluripotent stem cells can become more cell types than multipotent stem cells. In order to make them, viruses carrying small pieces of DNA called Yamanaka factors, which are c-Myc, KLF4, SOC2, and OCT4, or transcription factors, are inserted into a specialized cell. When these transcription factors enter the cell's nucleus, where DNA is stored, they integrate into the cell's DNA and begin to start making RNA, which is a type of nucleic acid, and that eventually will make proteins. Some of these transcription factors play a role in altering repressor proteins, histones, and methylation. As mentioned earlier, these changes would allow affected cells to gain access to the rest of the DNA. Other transcription factors like c-Myc in particular can increase the frequency at which cells divide. This allows induced pluripotent stem cells to regain that ability to reproduce rapidly, which is a key attribute of stem cells. There's one problem though. When cell replication is manipulated, there's always the risk that cells can replicate quickly and start becoming cancerous. This unfortunately is a big risk associated with these stem cells, and scientists are still trying to figure out how we can harness the power of these stem cells without increasing the risk of malignancies and cancers. In real life, the Yamanaka method has allowed scientists to create virtually any cell type in a laboratory. This has revolutionized the way we think about tissue repair and organ regeneration in the context of various medical diseases. It won't be long before we can cure type 1 diabetes by administering induced pluripotent stem cells into someone's defective pancreas. I believe it's likely that Adam introduces similar transcription factors into the host's body, which reprograms specialized cells back into stem cells. Having a replenishing supply of stem cells would confer the ability of Adam to regenerate tissues following an injury. But it's not all sunshine and rainbows with Adam and plasmids. They unfortunately have a very sinister side to them. Bioshock is full of splicers, Adam-addicted citizens who hunt the protagonist in search of their next Adam fix. According to the Bioshock wiki, a constant supply of Adam is needed to keep the stem cells stable in order to remain sane and healthy. The consumption of more Adam leads to the creation of more stem cells in the body, which completes a devastating positive feedback loop. Since Adam and plasmids alter the same transcription factors that the Yamanaka method uses, it's not a stretch to assume that the stem cells that are made are unstable and liable to become malignant cancers. It's also plausible to assume that the specialized cells made from Adam stem cells do not last a long time within the body. Remember that these stem cells are replacing regular damaged cells. Once the new specialized cells are gone, they need fresh ones to replace them. If there are no stem cells left due to a lack of Adam in the body, it could lead to massive organ damage and even widespread organ failure. This would explain the host of signs and symptoms splicers experience after continued Adam use, such as hair loss, jaundice, which is yellowing of the skin and could be related to liver disease, tumors, memory loss, hormonal imbalances, just to name a few. All of these signs and symptoms can be explained by a loss of cell renewal from prolonged Adam deprivation or too much Adam use in the case of a tumor or even a cancer. So that's it. That's how Adam and plasmids would work in the real world. If you enjoyed this video, please do consider subscribing, leaving a like or comment. It really does help the video get out there. And if you have any suggestions on what other video games you want me to cover the medicine behind, please do let me know, as I'm always looking for new ideas. See you guys in the next one.